Welcome to the Science of Sports Performance, where we discuss the real science of nutrition and exercise, helping you train smarter, fuel better, and perform at your very best. My name is Ben Pressler, and I'm currently an undergraduate student at Brigham Young University, majoring in both nutritional and exercise sciences. I'm pursuing my PhD with the goal of becoming a professor of sports nutrition. Today's episode is Nutrition 101. Today we're going to be talking about carbs and alcohol, carbohydrates and alcohol. Now, I decided that I wanted to do sort of a mini-series, Nutrition 101, and this is going to be the first episode of that mini-series, just because I feel like it's easier to understand, future topics and things that I'm going to be talking about in the show if we have sort of a fundamental understanding of just basic nutrition principles. So in all these different episodes, I am definitely going to hit on certain aspects of how, this information that I'm sharing can be applicable to sport and sports performance and to athletes. However, I really just want to dive into the sort of basic chemistry and biology, the very simple aspects of nutrition. So Nutrition 101. Probably the next several episodes of this podcast are going to be Nutrition 101, and I'm actually super excited for it. Today we're going to be talking about, again, carbohydrate and alcohol. So in this episode, you can expect to learn about sort of the basic structure and types of carbohydrates. We're also going to talk about all the different, there's nutritive carbohydrates, such as sugars and starches, but then we're also going to be talking about non-nutritive sweeteners, or you may have heard them called, of course, artificial sweeteners. We're going to talk about those. We are going to talk about different levels of carbohydrate intake, sort of what is recommended, how much carbs should you be eating in a day. Of course, there's a variety of answers to that question. And then we're also going to be talking about the many health benefits of fiber, why you should have a high fiber intake ideally. And then lastly, we are going to talk about alcohol, dietary alcohol. And really, we're going to be talking all about why you probably should not be drinking alcohol if your goal is to perform at your very best. It's something that I would recommend against. And with that, let's go ahead and get into it. First of all, a carbohydrate is one of the three macronutrients. There's macronutrients and there are micronutrients. The three macronutrients are carbohydrates, proteins, and fats or lipids. Proteins and fats are going to get their own episodes in the future. Today we're talking about carbs, and alcohol is technically a fourth macronutrient. Macro, of course, is a prefix that means something is large, whereas micro means that it is small. The macro and micronutrients, it doesn't have to do with like the size of, the compound itself or like the chemical structure of it. It has to do with the intake of the nutrient. So carbohydrates and proteins and fats we consume in gram quantities, often hundreds of grams of these macronutrients in a day, whereas the micronutrients, which are the vitamins and the minerals that we consume, you consume those in very small quantities. The quantities of those are going to vary greatly depending on what they are. However, it's usually less than a couple grams. Sometimes it's even milligrams or micrograms, those micronutrients. And like I said, all of those are going to get their own future episode as part of this Nutrition 101. Today we're going to focus on carbs, and at the end, a little bit about alcohols. Now, carbohydrates, they always pretty much come from plants in our diet. And maybe that's probably intuitive or something you already know or have figured out, but glycogen, which is something we're going to learn about in better detail here in a second, but glycogen might be something you're familiar with. It is the storage form of carbohydrate in the human body. There are glycogen stores in muscle tissue and in the liver. So how come, when we eat a cow, we eat beef, who, they have glycogen stores in their muscle for energy. How come we don't get any carbohydrate from eating like a steak if there's carbohydrate in the muscle? And the reason for that is just because after the animal passes away, that glycogen that is in the muscle is going to very rapidly deteriorate and just kind of break down into not a carbohydrate anymore. So it's not something that we are going to be able to consume. We're not going to get any dietary carbohydrate from animal sources. Maybe you could argue that if you were to kill an animal and then consume it very, very quickly thereafter, maybe you'd get a little bit of glycogen. However, especially in like the cooking process, assuming you're not eating the animal raw, in that cooking process, you probably are going to further up that process of destroying that tissue glycogen stores, and really there's going to be no carbohydrate from animal sources. And I think that's something that you already know, but it's something to think about, something that's cool to understand. All of our carbohydrates are pretty much going to come from the sugars and the starches, the structures of plants. So that can be fruits and vegetables, or it can be grains like wheat and corn and oats and rice. Carbohydrates, the structure of themselves, if you think about that name, carbohydrate. Well, carbo is just one letter off from the element carbon. If you're familiar, when we're talking about organic chemistry, in chemistry and in science, when we say that something is organic, we're not talking about, it's a crop that was made without any pesticides. Organic just means something is carbon containing. So all of the molecules in our body are carbon containing. DNA and protein and sugars and everything is carbon containing, so it is considered to be organic. So yeah, carbo and carbohydrate just means carbons. Carbons are very important for human life, and that's what carbohydrate means. And then hydrate. When I say hydrate, what do you think of? You're thinking of water. You're drinking water to hydrate. And that's actually exactly what a carbohydrate is. It is one carbon and one water molecule. Not just one, but in that ratio. So going back probably to middle school, you've probably learned about photosynthesis, and you've learned about how plants, with the energy of the sun and water and carbon dioxide, are able to produce their own glucose for energy. And that glucose has the chemical formula of C6H12O6. Water, of course, is H2O, so that H12O6 is actually just 6 water molecules, and then there are 6 carbon molecules. So a carbohydrate really is some molecule with a ratio of 1 carbon molecule and 1 water molecule. And within those bonds, within those molecules, are going to be stored the energy that we get from eating these carbohydrates. 1 gram of carbohydrate is going to yield 4 calories. Whether it's from sugar or whether it's from starch, it's still going to yield in the same amount of calories. Fats contain 9 calories per gram. The reason that fats contain so many more calories than carbs per gram, more than double, is because there's not a lot of hydrate, right? There's really not any, because fats are not water soluble. They don't have those water molecules attached to them. They're mostly carbons. So there's going to be a lot more energy stored in those carbon-carbon bonds than in carbohydrate bonds. And so carbs and proteins have 4 calories per gram, and fats have 9 calories per gram. Up to now, hopefully you're following. We haven't gotten into anything very complicated at all, but that's the basics of a carbohydrate. Carbohydrates, basically in all of their forms, are chains of molecules called saccharides. Now, a saccharide is basically just the fancy scientific chemical name for a sugar. Now, there are monosaccharides, there are disaccharides, there are polysaccharides. There's even something called oligosaccharides, and that just has to do with how long the chain is. So mono means one, of course. So a monosaccharide are the base units of sugar. And those 3 molecules, there's 3 different options, are glucose, one we're very familiar with, fructose, something I think we also are very familiar with, and galactose. Those are the 3 monosaccharides. There are also 3 different types of disaccharides. Di means 2. It's a prefix that means 2. And so a disaccharide is 2 of those monosaccharides linked together. There are also 3 different types of disaccharides. The first one is sucrose. That is something we're all super familiar with. That is table sugar, just white sugar that you add into your coffee or tea, or you mix into cookies when you're making them. That is sucrose. So that is a disaccharide consisting of one glucose molecule and one fructose molecule. Another disaccharide that you're probably familiar with is lactose, or milk sugar. That is a disaccharide consisting of glucose and galactose. And then the last kind of disaccharide is something called maltose, which is a disaccharide of just two glucose molecules linked together. Now, going back to those monosaccharides, as I already mentioned, the formula for glucose is C6H12O6, something you probably already know. Now, that C6H12O6 is actually the same chemical formula for all three monosaccharides. That's the formula for glucose and for fructose and for galactose, but they're oriented a little differently. Now, if you've taken a college-level chemistry course, maybe you know this from high school chemistry, but definitely if you've taken a college-level chemistry course, you are familiar with something called an isomer, and in this case, something called an enantiomer. Those words aren't super important, but basically it just means that we can have molecules that have the exact same chemical formula, but just because they're arranged differently, they could have completely different properties. It's basically the scientific equivalent of a homograph. And so that is, in English, we have, words that can be spelled the exact same way, but they are pronounced and have completely different meanings. So an example is LEAD could mean the metal lead, or it could be pronounced lead as in leader, someone who leads a group or leads a pack or whatever. LEAD is homograph, and these isomers are kind of like those homographs. So the exact same formula, but different orientations. They're pieced together differently. They're in different orders. Because of that, they can actually have very different properties. And one extreme example that we learned about in my chemistry class is something called thalidomide. Thalidomide was a medicine. I believe it was made in the 50s or 60s. And it's a medicine that was actually prescribed to pregnant women to help treat their morning sickness. There's that nausea you experience as a pregnant woman. I'm not super familiar with that, but it was prescribed to help women with their morning sickness, help get rid of some of their nausea. And it is a good medicine. It is a great medicine that helped those women with that. However, it had two different configurations called enantiomers. An example of an enantiomer is your left and your right hand. They have the exact same amount of bones. They are actually kind of put together in pretty much the same order, but they're just not the same. They're mirror images of each other. So my left hand, though it has the exact same structure of my right hand, it's just put together in the mirror image of each other, so they're different hands. They just are not going to work the same. If I get a pair of gloves, I can't really wear the left one on my right hand and vice versa, just because it's not going to work. Well, the mirror image of this thalidomide medicine actually turned out to be a teratogen, which is a medicine that is able to cross from a pregnant mother to a baby and cause birth defects. So that is actually super, super bad. It's a very, very extreme example of how these things can have different effects. One literally is being prescribed to help these pregnant mothers, while as the other one with the exact same formula, just the mirror image, is a teratogen that can harm the babies. So I actually don't know if this medicine is still for sale, but they just do a better job of testing and making sure that it is only the configuration that they like, or if it's completely gone off the market for those reasons. But that is an example. I wanted to go into that. That was definitely sort of a tangent, but to understand that is definitely going to help us understand maybe why some of these molecules behave differently in the body and in different foods and things like that. Now, one thing that you should be aware of next is the difference between an alpha and a beta bond. That is, alpha is in the letter A and beta is in the letter B. You don't need to know the exact chemistry of these alpha and beta bonds. I don't want to go into that in detail in this, but you just need to know that alpha bonds are easy to break and beta bonds are hard or sometimes impossible to break. So understanding that, let's go back to the disaccharides that we talked about. Again, that's going to be sucrose, lactose, and maltose. Well, so sucrose is a glucose linked to a fructose, like I've mentioned, and they are connected with an alpha bond. Alpha bonds are easy to break. So when we digest sucrose, the digestive enzymes, amylase and sucrase, are able to break the glucose and the fructose molecule apart very easily. We're able to digest it very easily. If you consume sugar, it's going to probably spike your blood glucose very quickly because it's absorbed very rapidly. Those alpha bonds are very, very easy to break. Let's think about then lactose. Lactose, which some of you, of course, have heard of because some people are lactose intolerant. Now, lactose, again, is a glucose linked to a galactose. However, that glucose and that galactose molecule are linked together with a beta bond. Again, those beta bonds are very hard to break apart. And so that is why if you do not produce the adequate amount of the enzyme lactase in your intestines, you're not going to be able to break that lactose molecule into the individual monosaccharides. It requires that specific enzyme to be able to break that beta bond. And if we don't make enough of that enzyme, then that lactose is going to pass into the large intestine where there is our gut microbiome, lots of bacteria in there that can be very, very good. However, when they get that lactose sugar, they are going to break it apart and ferment it in such a way that causes a lot of gas, bloating, can cause diarrhea by drawing extra water into the digestive tract. And that is why people who are lactose intolerant have, just all sorts of gastrointestinal issues after they consume lactose. Now, you can consume, if you have lactose intolerance, a pill called Lactaid, which is just lactase, the enzyme lactase. So if you consume additional, exogenous lactase before you consume a food that contains lactose, then there you go. You're supplementing your body's ability to produce the lactase enzyme, and then it's probably going to be broken apart and absorbed into your bloodstream and used for energy rather than causing those gastrointestinal side effects. Another type of bond that you should know of, it has less to do with actually the type of bond. It's not alpha and beta, but rather it just talks about the location of the bond. The two types of bonds in carbohydrates are going to be 1,4 bonds and 1,6 bonds. Again, that talks about the location. And what those numbers mean is actually just which carbons of those monosaccharides are linked to each other. So a 1,4 bond, 1,4 bonds make straight line chains. And so that just means that the first carbon of a glucose molecule is connected to the fourth carbon of another glucose molecule. Now, the 1,6 molecule is where these polysaccharide chains, poly meaning many, so a polysaccharide is a very large carbohydrate with lots and lots of these individual monosaccharides. Well, a 1,6 bond is just the first carbon is linked with the sixth carbon of another monosaccharide, and that creates a branch. So these polysaccharides, they can be in a straight line. However, oftentimes they are branched, and in the straight segments, they are all 1,4 bonds, and at all of the branch points, where a different branch comes out of that chain, it is going to be a 1,6 bond. So an example of those branched carbohydrates are amylose and glycogen. Amylose is a starch. Now, maybe I skipped over. They're growing in size. We have sugars. Sugars are mono and disaccharides. And then there are starches. So something like, wheat or corn or potatoes, those are going to be starches rather than sugars. Think like bread flour and all those different things. If it's a carbon or a carbohydrate source that's not sweet, it's going to be a starch. Now, those starches are polysaccharides. They have lots and lots and lots of these saccharide molecules. Amylose is just the actual chemical name for starches that we consume, amylose. And then glycogen, as I've already mentioned, is the storage form of carbohydrate in the muscle tissue and in the liver. Both of these are very, very branched. So they have lots of straight line segments, but they look like a big bush or a tree just full of these branches. these very long and complex structures. Now, glycogen is just branched so that we can fit as many carbohydrates into one space as you can. And then, when we need to use that muscle glycogen for energy, it's just, a bunch of glucose molecules connected with 1,4 and 1,6 alpha bonds. And then those glucose molecules can be broken off the end very quickly and very easily, so we can use those for energy. Amylose is actually, both amylose and glycogen are very water soluble. Just because they have so much sort of surface area, there's lots of places where water can bind and attach and fit in these different spaces. And so amylose is actually a common food additive. You might see that on, any variety of certain sauces and condiments and all sorts of foods. I challenge you to look at some of your nutrition labels and see if you find amylose as a food additive. Now, that is used as a thickener just because it's able to, kind of hold on to so many water molecules. It's able to make, sort of a thin, watery sauce, very viscous and thick, which is very desirable in cooking and in these, food additives. It's a very simple way to make a sauce, thicker, as opposed to having to do any sort of like cooking and adding, other sugars and things like that, so you can get a better texture that you like. And I think that's a great example of, food additives are not always bad. And that's a thought that we're going to get into later. But this amylose is literally just food starch that we eat all the time. And just because of its chemical structure, we're able to use it for another purpose in things like sauces and condiments. The next, after starches, is fibers. So sugars, starches, fibers. As I mentioned, the starches are just these big polysaccharides connected with alpha bonds. And then, can you guess what a fiber is then? Because you probably know that fibers are not digested. There's my little hint. Fibers are polysaccharides that are connected together with beta bonds. Again, beta bonds are hard to break. Fiber is not digested. That's actually one of the reasons it is good for us. We're going to get into the benefits of fiber later in the episode. But fiber is just basically a starch, except it's connected with beta bonds rather than alpha bonds. Now, some examples of fiber is like cellulose. Cellulose is the carbohydrate substance that is used for a plant to construct its cell wall. The cell wall of a plant is built with cellulose. There's also things like lignin. Lignin is actually basically wood. So it's not very, dietary. It's not something that we're going to get any calories from, and probably you don't want to eat like sawdust. I'm not advocating that you eat, sawdust or anything so that you can get lignin because it's fiber. That's bad. However, there are some naturally occurring sources of lignin in food. For example, if you've ever cooked asparagus, maybe you know that the bottom section of asparagus is very, very tough and very, very hard. So it's common before you cook the asparagus to snap that off. Usually it snaps off pretty easy because it's so stiff and, it's basically inedible for that reason. Well, the reason that happens and the bottom of that asparagus gets so stiff is because, as it is, been picked and is transported and all these different things before you eat it, some of those carbohydrates in the bottom of that asparagus stalk are converting into lignin. There you go. There's one example of dietary lignin. Now, again, I don't advocate that you go and eat lignin because it could just, We do eat some amounts of lignin in vegetables and things like that, but it's not something necessarily that you want to seek out. So that cellulose and lignin are examples of insoluble fiber. That is fiber that does not dissolve in water, but then there's also soluble fiber. So kind of similar to like amylose, how I've mentioned that it can be used as a food additive because it's a thickener because of its branched structure. There are also things like pectins and gums. And these are just all sorts of, things that are found in plant products. So cellulose and lignin, for example, are commonly found in like the bran of a seed or a grain. So you're going to get these fibers in whole grain foods, whereas if you're eating just refined grains where the bran and the germ of the grain or the seed has been removed, then you're not going to be getting basically any of that fiber. Now, some soluble fibers that are found in plant products, where various places in different fruits and different grains, we're not going to get very far into that, but things like pectins and gums are used also as food additives. Maybe if you guys have ever made like homemade jam or jelly, then it's common to add in, a little packet of pectin. And that pectin is a soluble fiber that, very similar to amylose, is able to thicken up that jam very naturally. There's also, things like gums that are found, again, in these grains and in these fruits. And that is another one that you might very well see on a food label, in a sauce, or all these different sorts of foods. If you see pretty much any sort of a gum, of course it doesn't mean chewing gum, that is just a soluble fiber that can be found in foods. Now that basically covers sort of our nutritive carbohydrates, again, sugar, starches, fibers. What I wanted to talk about now is non-nutritive sweeteners. These can be called artificial sweeteners, except that's kind of a misnomer. It's not the greatest way to say it, just because there are some, natural non-nutritive sweeteners. So for example, like stevia plant and monk fruit extract, those are natural, but they are non-nutritive. They're considered non-nutritive. Now, non-nutritive sweeteners work just because they are some sort of a compound that bind to the sweet receptor on the tongue. Not to get into, a lot of the anatomy and physiology of the tongue, but of course there's different, sorts of taste receptors on the taste buds of the tongue. Some of them taste for salt, some of them taste for sourness and bitterness, and of course some of them taste for sweet. Now, the sweetness, the sweet receptor on the tongue, is going to be activated by aromatic groups. And aromatic just means that something has a ring, a 6-carbon ring. And that is, glucose and galactose actually have that 6-carbon ring. Fructose, actually, though it has the same structure, actually has a ring consisting only of 5 carbons. However, that ring really is just what kind of signals for sweetness. And so there are ways that we are able to, make these structures that have that ring structure in them, the aromatic ring, that are not nutritive. There's a couple different examples. Well, so some of them that you might have heard of are like sugar alcohols. Those are commonly found in gum, like actual chewing gum. I know we just talked about gum that's not chewing gum, but sugar alcohols are commonly found in chewing gum. Aspartame is one of the primary artificial sweeteners used in diet sodas. Saccharin is also known as Sweet and Low. That's the pink packets that people can add to their coffee and their tea or whatever. There's also sucralose is a very common one. And then there are some natural ones like stevia leaf extract and monk fruit extract. There's more. There's lots and lots and lots of artificial sweeteners, but those are some of the basic ones. Now, there are actually 2 different ways that a sweetener could be non-nutritive. Now, the first one is one that actually it does have calories, but it's so much sweeter than plain table sugar that you don't need to add very much at all. So the calories that you get from it are basically negligible. So an example of that is aspartame. So aspartame is the methyl ester of the dipeptide. And these are terms that I haven't taught you about because that's going to be in the protein episode, but it's a dipeptide of aspartic acid and phenylalanine. So dipeptide, peptides, well, actually are kind of like the disaccharide equivalent, or the polysaccharide equivalent of proteins. So the building blocks of proteins are amino acids. When you have several of them put together, they are called peptides. I'm actually thinking I need to perhaps backtrack right now. There is something called an oligosaccharide that I forgot to kind of teach you guys about. An oligo means several or a few. And so an oligosaccharide, it's more than 2, so it's not a disaccharide, but it's not like very, very long. Usually they're probably 10 to 15 saccharide molecules. And so oligosaccharides can be connected with a variety of alpha and beta bonds. And so they can be kind of tricky to digest, and some get digested well and some don't. Oligosaccharides are commonly found in like beans, like black beans, pinto beans. And that is actually the reason why some people will say that when you eat beans, it's going to give you gas and it's going to make you fart. It's because, well, it has, those beta bonds, similar to how lactose has that beta bond that struggles to get broken apart. Some of those are going to make it to the large intestine where they are fermented by the bacteria and, produce different gases as a byproduct of that. And so just how you can consume a lactase enzyme pill, you can actually consume different digestive enzymes that are going to help you break apart those oligosaccharides. So you can actually buy pills called Beano that you can eat whenever you eat beans if that causes gastrointestinal discomfort that you don't want to have to deal with. Anyways, going back to aspartame, I apologize for that tangent, but aspartame is basically it's a methyl group added onto a dipeptide, so 2 amino acids, those amino acids being aspartic acid and phenylalanine. Phenylalanine has that aromatic group, and that's why it's gonna taste sweet to the tongue. However, aspartic acid and phenylalanine, those are found in meat and in protein sources. Those are calorie-containing amino acids, but aspartame is super, super, super sweet to the tongue. Now, I don't have a great answer to you as to why. This is something I definitely looked into and read some of the scientific literature about it. How can a chemical be so much sweeter than sugar? Some of these artificial sweeteners are tens, hundreds, even thousands, in some cases, thousands of times sweeter than plain sugar. And basically it just has to do with, the chemistry of that aromatic group and the different, elements and molecules that are bound to it. Sometimes they will just have a much greater affinity. It's much easier for them to be attracted to that sweet receptor and signal that sweet taste, and so they can be much, much sweeter than sugar. So aspartame, for example, there's only about 200 milligrams of it in 1 can of diet soda. So that is 1/5 of a gram. 1 gram of protein, just like carbohydrate, yields 4 calories. So that is going to be less than 1 calorie. In fact, it's going to be 0.8 calories in 1 diet soda. Now, so if you did consume perhaps 10 diet sodas in 1 day, then you've consumed 8 calories. So they are technically nutritive, but I'm sure it's easier for you to tell that this is a negligible amount of calories. It's not really something that we need to be worried about. For that reason, it is considered non-nutritive. Now, that is how some of these things work. Now, the other option is that a non-nutritive sweetener could be metabolically inert. Now, basically, that just means that it is not broken down at all, so we do not get any calories from it genuinely 0 calories. Now, some examples of this, first off, is sucralose. So sucralose is basically a sucrose molecule, except some of the hydroxyl groups, which is an oxygen and a hydrogen, some of those hydroxyl groups on that sucrose molecule, in the case of sucralose, have been replaced actually with a chlorine. And so just because of that, the sucrase enzyme is not able to attach to the sucralose molecule and break that alpha bond. We're not able to get any calories from it. It is metabolically inert. It's not digested by the body. So although it signals a sweet taste, there's no calories that come from it. Sugar alcohols are actually the same way. Now, sugar alcohols are not genuinely alcohol, like the kind of alcohol that we consume in beer and wine and liquors. What it has to do with, it kind of gets into some organic chemistry that is not necessarily understand, but there is certain molecules, just like I described, like the hydroxyl is an OH, and the chlorine, these different molecules that you can attach. Basically, a sugar alcohol is a sucrose molecule that has been replaced with a group that is called an alcohol, though it's not the same as the ethanol that we consume, again, like I said, in beer and wine and in liquors. So it basically works exactly the same as sucralose does. Some of those hydroxyl groups have been replaced with these alcohol groups, and because of that, it is metabolically inert, and we don't get any calories from it. Sugar alcohols are very commonly used in chewing gums because the bacteria in our mouths are not able to break them down. Now, the reason we get cavities from excess sugar consumption is just because when we have those sugar molecules and carbohydrate molecules in our mouths, the good and healthy bacteria that we are supposed to have in our mouth Well, they can actually break down those molecules, and then they create acidic byproducts. And those acidic byproducts of those bacteria breaking down those carbohydrates are what is going to, wear down the tooth and lead to cavities. So sugar alcohols, though they do taste sweet and you can use them to flavor a chewing gum, are not going to contribute to those, sugar molecules that could lead to cavities. So if you're going to be chewing on gum all day, it is much more desirable to be chewing on something that has just a sugar alcohol rather than, full sugar gum, which could definitely contribute to cavities and bad oral health. Now, non-nutritive sweeteners, it's actually kind of interesting. The first several were actually discovered by accident. Nowadays, I'm sure that there are scientists in labs that are kind of devoted to finding new and safer and better artificial sweeteners. However, the first several were completely discovered by accident, usually by scientists who forgot to wash their hands. So the first ever discovered artificial sweetener was saccharin, or Sweet and Low, those pink little packets of artificial sweetener. And it was actually discovered by a scientist who was working on some sort of, he worked with coal, and he wanted to come up with these different chemicals that could help in the process of processing coal for use. I don't know much about coal. I know a lot about nutrition, not a lot about coal. So I don't know what the process was. But basically, in his process of trying to find these chemicals as he was working with coal, he forgot to wash his hands. He went to eat his lunch, and then he noticed that something that was on his hands tasted sweet. Now, obviously, there could have been a lot of possibility for that being very toxic and very deadly for us, but it didn't work out that way. And so we discovered saccharin. He identified that molecule as saccharin. Aspartame was actually discovered the exact same way by a scientist who was doing cancer research. He was trying to find and create medicines that would help combat cancer, and he forgot to wash his hands. And that's like pretty dangerous, If you're working in the lab with chemicals and you don't wash your hands and you get some of those chemicals on your food, that could be pretty bad. So definitely advocate for everybody washing their hands after they get out of a scientific lab. But, we stand to benefit from the fact that they didn't, and he discovered aspartame in that fact, which is, pretty cool. But it does beg the question, are these artificial sweeteners safe? They're discovered by accident in many cases in a lab. What are the odds that these things are really safe to consume, every day and in large amounts? Like, are these things really safe for consumption? And the answer that I'm going to give you is yes. If you want a straightforward answer, there it is. The answer is yes. Now, I am positive that there have been many, many artificial sweeteners that go to hit the market and then they are found to be pretty deadly. It's a very big risk or it's a very big fear, maybe I should say, that many of these artificial sweeteners are carcinogenic. They are cancer-causing. And I think that is well-founded because I'm sure that there have been many of these that have been found to be carcinogenic, but that doesn't mean that all the other ones are. We do extensive testing, and the FDA does extensive testing on these artificial sweeteners before determining whether or not they are safe for human consumption. Now, something funny as well about saccharin, it's already funny that it was discovered by some dude who was working with coal. But another cool thing about saccharin and in its history is that this was discovered in, I believe, the late 1800s or the early 1900s. So it was a long time ago. After it was put into the market, they were doing more rodent testing, and they discovered that the rodents that they were giving this saccharin had higher amounts of bladder cancer. They were developing cancer in their bladder and in their kidneys, their urinary tract. And upon further investigation, they found that there was a lot of damage. There was a lot of sort of like cuts and just cellular damage to the cells of these rodents' bladders. And that damage and having to repair and regrow cells and constant damage and regrowth is what led to this bladder cancer in the rats. And so there was huge fear of that, and saccharin was pulled out of the market. They didn't sell saccharin anymore because they were worried about it causing bladder cancer. However, eventually, they realized that rodents metabolize saccharin differently than humans do. So I mean, that's one of the cons of using rodents for research. We can gain a lot of valuable insight, but it's definitely not, factually applicable in all these different circumstances to humans. And so, well, anyways, when these rodents were metabolizing saccharin, it created this very crystalline structure that was very sharp, and that is what it was excreted in the urine, and it kind of cut up the bladders of these rodents, and that is what was causing the damage and the regrowth and eventually the cancer. However, we were able to prove that humans do not metabolize saccharin in the same way. We do not form that crystalline structure, and saccharin does not increase the risk in humans of bladder cancer. So, after that was understood, saccharin was placed back on the market. Now, on the subject of rodent testing, again, I don't care to get into the ethics of whether you think we should or should not be doing, testing on rodents. That's a question maybe that should be begged, but it's not what we're going to talk about in this podcast, or at least this episode. Anyways, these artificial sweeteners are tested on animals and oftentimes rodents, and we give them to these rodents at levels that really are very far beyond what you could ever consume as a human. But then what we get in, the level of concentration and, it's usually in milligrams per kilogram of body weight. So rats usually are going to be less than a kilogram or maybe a kilogram depending on the size of the rat. But so it doesn't take a lot of these sweeteners for them to get very high concentrations. Anyways, we feed these sweeteners to rats in different, levels and concentrations of milligrams per kilogram. And then we come up with something called the NOAEL. I don't know if anyone says it out, but the NOAL, whatever. It's the No Observed Adverse Effects level. So it's the level of consumption in rats at which no adverse effects were observed. So technically, this is the level that was safe for rats. Well, we take that NOAEL, and then we take 1% of it. And that 1% of the NOAEL gives us then the adequate daily intake. And so the ADI, adequate daily intake, is something set by the FDA and is considered to be safe for consumption every single day forever across somebody's lifespan. I apologize. So again, 1% of the NOAEL. So that really is, there's a huge margin of error in there. It's 1% of that NOAEL to get the ADI, and it's considered safe. That's going to be different for all these different artificial sweeteners because of their properties and everything. Some of them have a higher and some of them have a lower acceptable daily intake. But really, they are pretty hard to consume, even at the level of that ADI. So I wanted to give you an example that I did the math for here in my notebook, but aspartame, again, that is the one found in diet soda. There's a lot of hype and a lot of buzz around, diet soda and Diet Coke, causing cancer. And some people will say, well, there's no point in consuming Diet Coke because, yeah, maybe the full sugar Coke will make you fat, but the Diet Coke will give you cancer. Well, let me go ahead and say that those ideas are completely unfounded. Diet Coke does not cause cancer. As of right now, that is a hill I will die on, just because I'm sure that I have a little bit of bias in my mind because I do love to consume Diet Coke. Maybe I acknowledge my bias. However, all of the research really does point to the fact that these things are safe, or else I would not be drinking them. Anyways, the example. So the acceptable daily intake, the ADI, which again, as a reminder, is set at 1% of the NOAEL. The ADI for aspartame is 50 milligrams per kilogram of body weight per day. So for the sake of easy math, if someone was 100 kilograms, which is about what I weigh, if someone was 100 kilograms, they could consume 5 grams of aspartame every single day. Now, again, aspartame is primarily found in drinks and diet sodas. So if I was, as a 100-kilogram guy, what would I need to do to consume 5 grams of aspartame? And the answer is I would need to consume 25 cans of diet soda a day. every single day. So that is almost, by the way, 2.5 gallons, almost 2.5 gallons of diet soda in a day. So basically, I would not drink any water ever, and I would still be drinking an incredible amount of fluids in a day of nothing but diet soda to hit that acceptable daily intake. So I hope you can see, I like to use that example just because you really don't need to be so worried. Like, I have a diet soda, I have one every day, I'd say. Sometimes I have two, maybe sometimes I'll have three, but that's not super common for me. I certainly am not going to have 25 cans a day, which is what would be required for me to hit that ADI. Now, obviously, somebody who weighs less than me, somebody who was 70 kilograms, for example, that number is going to come down from 25 to maybe 17 or 18. But, I mean, you could still tell that is a very high level of aspartame and diet soda consumption. So it's not really something that we need to be super worried about in that regard. Now, the last thing I want to talk about in regards to non-nutritive sweeteners is that you should know that many non-nutritive sweeteners are not heat stable. So saccharin and aspartame, both the examples that I've kind of discussed, are not heat stable. Meaning, if you heat them up, whatever it is that you're trying to sweeten, oftentimes they will break down. Saccharin actually gets kind of bitter, which is frankly the opposite of sweetness after it is heated. And aspartame loses its sweetness when it is heated. So I use saccharin on a daily basis, I would say. I use it to sweeten my oatmeal. That's my favorite carb source. I mean, on the topic of carbohydrates, I love to eat oatmeal. And I use saccharin to sweeten my oatmeal. However, if I put in the saccharin, with the oats and with the water, and then I put the bowl into the microwave, well, then the saccharin is going to be heated to a very high temperature, and it could cause my oatmeal to be bitter rather than sweet. So I cook the oatmeal, take it out of the microwave, and then I add in the saccharin. Maybe there's going to be a little bit of breakdown in that regard, but definitely not as much. It's going to still be sweet. So that's something, if you hope to use these artificial sweeteners, is probably something you should keep in mind. Actually, one thing that just came to mind because talking about those little pink packets of saccharin is one of those things that is metabolically inert, and it is much, much sweeter than table sugar. So those little pink packets of Sweet and Low are 1 gram in total weight, but it's not 1 gram of saccharin. I think it's about 100 milligrams of saccharin. So it's about 10% by weight saccharin. And then the rest of it is dextrose. And dextrose is actually sort of the alternative name for glucose. Dextrose, in medicine and in even in Gatorade, if you look at the ingredients label on Gatorade, it'll say that it contains dextrose. That just means glucose. I've looked it up as to why it has that, alter ego called dextrose, and it actually has to do with the fact that it reflects light in a certain way, which doesn't make sense to me. But just know that when you hear dextrose, that means glucose. And so it actually has 0.9 grams, 90% by weight, glucose, which is a nutritive sweetener. And so one packet of that Sweet and Low sweetener actually has about 3.6 calories. Now, it gets a lot of sweetness for that 3.6 calories. So, it's not a huge deal, but Sweet and Low is able to say that it is 0 calorie because the FDA lets you say that something is 0 calorie if it's less than 5 calories. And so maybe that's something you want to keep in mind. If you consume 100 packets of Sweet and Low every single day, well, then you should know that you are actually consuming 360 calories every single day. But 100 packets is insane. I think I use maybe 5 in my oatmeal, so it's maybe almost 20 calories of sugar in there, which for the sweetness that I'm getting out of it is a happy trade-off. I'd still much rather use the Sweet and Low as opposed to full sugar. Next, I want to talk about carb intake. How much carbohydrates should we be eating in a day? Well, the first number I want to throw out at you is the RDA, or the recommended daily intake set by the USDA for carbohydrates, is 120 to 130 grams. It is not, grams per kilogram or anything like that. Doesn't matter who you are, the RDA is 120 to 130 grams, 130 grams of carbohydrates, which again, with 4 calories per gram, that's going to be 520 calories, so 480 to 520 calories of carbohydrate. And that is the number set that our brain and our central nervous system, our spinal cord, need in a day so that they can function. The brain prefers to run on glucose. It can run on ketone bodies if we are not consuming carbohydrates. However, it definitely prefers glucose for energy. And so just for brain function, 120 to 130 grams per day is the RDA for an adult in the United States. Now, with that guideline in mind, we're able to probably better frame different carbohydrate levels of diets. There's lots and lots and lots out there. I'm sure you guys are familiar with like the ketogenic diet, the Atkins diet, these very low carbohydrate diets. Now, if you're not consuming carbohydrates, your body can utilize fat and, ideally body fat for energy, and it's going to be able to produce ketone bodies to feed your brain. You do not need carbohydrates to survive and for your brain to run. You definitely can survive and do well on a ketogenic diet. However, it's not necessarily something that I recommend, especially not for athletes. We'll get into that later. I wanted to just kind of frame my personal opinions on what these different carbohydrate consumption levels mean in different diets. This is not something that has been well established. Different people have different opinions on what like a low carbohydrate versus a high carbohydrate diet is. Oftentimes when you read a paper about this topic, the author who is writing will kind of give their opinion and what they suppose and the levels that they are going to associate in their paper or whatever. You're going to get that opinion. I'm going to give you mine at this point. And my opinion is that a very low carbohydrate diet, or a VLCD, if you read the scientific literature, you're going to see those acronyms, VLCD, very low carbohydrate diet. To me, that is 50 grams of carbohydrate or less. I believe the ketogenic and the Atkins diet recommend 25 grams or less of carbohydrate in a day. The reason they give you that 25 is just because if you're eating vegetables, you're going to get a little bit of starch and a little bit of carbohydrates from your vegetables, but it's good to eat vegetables. But that is a very low carbohydrate diet. To consume less than 50 grams of carbs in a day, that is what I consider very low. Then I consider a low carbohydrate diet, about that RDA of 120 grams. So I consider that low because that is the level set just to fuel your brain and your nervous system. And so technically speaking, on top of that, you haven't used any carbs for fueling your activity and your exercise and anything. So for me, a low carbohydrate diet is about 120 grams or less per day. Then a moderate carbohydrate diet, at this point, we can't give you, just a number of carbohydrates, but at this point, it's probably going to be grams per kilogram of body weight. Again, I weigh about 100 kilograms. I consider a moderate carbohydrate diet intake 3 to 4 grams per kilogram. So for me, that would be about 300 to 400 grams of carbohydrates. And then a high carbohydrate diet, I consider 5 plus grams of carbohydrate per kilogram of body weight. So for me, that would be 500 plus. Now, you should know, though, depending on your sport and your activity level, like ultra marathon runners, endurance athletes, this level could be way, way higher than 5 grams. It could be 10, it could be 15 grams of carbohydrate per kilogram of body weight. When you're so active, if you're doing, hours and hours of this long endurance training, but just for me personally, about 5 grams per kilogram is when you kind of enter that high carbohydrate diet threshold. But just, I want you guys to understand that it could be much, much, much higher than that. Maybe they should make a VHCD, a very high carbohydrate diet. Maybe I'll pen that in when I start writing scientific papers one day. There are other guidelines for carbohydrate consumption that are not just, on that scale that I've described, but rather a percentage of the calories that you eat. So, for example, 2,000 calories is a common nutrition guideline. You'll see on food labels that 2,000 calories a day is given for nutrition guidelines. Anyways, say someone is eating 2,000 calories a day. There are other guidelines that say you should be consuming maybe 30 or 40 or 50% of your calories from carbohydrate. So let's say you were consuming 50% of your calories from carbohydrate, and then, maybe 30 from protein and 20 from fat. There's different models that people like to do for that percentage-based diet. But if you were consuming 50% of your calories from carbs, you're eating 2,000 calories a day, then you're consuming 1,000 calories of carbs, which divided by 4 is 250 grams of carbs. I want to talk about some of the benefits of dietary fiber. Recently, in the past couple of years, the carnivore diet has become very, very popular. It's kind of the new trend. And one of the cons of that diet is that it is very low in fiber because you're not eating grains or fruits or vegetables. You're only eating plant products, or sorry, not plant, I apologize. You're only eating animal products. It's a carnivore diet. And as I've already mentioned, you don't get any carbohydrate, including fiber, unless you're eating plant-based foods. I'm not saying that you need to have a plant-based diet, but in order to get fiber, you need to eat plant-based foods in addition to the meat and whatever else you might be eating. Anyways, fiber is one of those few things in nutrition that we are just super, super confident about, right? There's lots of things that are considered bad for you and are considered good for you. Some of those things kind of bounce back and forth. For example, like cholesterol, dietary cholesterol, it used to be like really, really bad. And now some people consider it to be like not that bad and maybe kind of good for you. But then there's also different types of cholesterol and all of which one's really bad and, is saturated fat the contributing to cholesterol. Anyways, not to get into that in this episode, but there are lots of things that we have a pretty good idea on, but there's just a lot of variability. Fiber is not one of those things. Basically, any of the literature that is worth reading, well-designed study, etc., any of that literature discussing fiber finds good health outcomes, and that is across, cohort, long-term studies. It is based on, randomized control trials of giving people fiber and analyzing their blood work changes. Fiber is definitively pretty good for you, and I can confidently say, according to the science, that you should be eating fiber. Fiber is very, very good for you. Well, why? Why is fiber good for you? Why is it so magic? Why? Well, that's a good question. We've already talked about how there's soluble and insoluble fiber. Going into that, you're going to get different health benefits from the both of them. But in a nutshell, fiber is going to help you with your digestive health in a number of ways. First off, it is actually going to feed mainly the insoluble fiber that is fermentable by the bacteria in your gut. It is going to feed the bacteria in your gut. Now, that is something that is considered a prebiotic. You can consume a probiotic, which is where you're actually consuming bacteria that you are hoping will implant themselves in your gut through yogurt and fermented foods like kimchi and sauerkraut, for example. However, a prebiotic is a really, really good idea because, sometimes a probiotic might just introduce 1 or 2 strands of bacteria and maybe it's not super compatible with your microbiome. I know that you can do testing on your microbiome, but it's probably expensive and you have to, poop in a cup. It's probably not something that many people want to do. But if you just take a prebiotic and you feed the bacteria that are already in your gut, you're going to be able to strengthen them, give them the tools that they need to be healthy for you to have good digestive health. The other reason it can be good for your digestive health is because it's going to add bulk to your stools. Now, insoluble fiber is going to do that, but definitely soluble fiber is going to do that. Because again, soluble fiber is able to mix with water and form this sort of gel-like consistency, and that is going to just be very, very, add bulk to your stool, to your bowel movements, but it's going to be very smooth. It's going to, I don't mean to get too graphic as we're talking about your bowel movements, but soluble fiber can just help, add a little bit of bulk to it, which helps that, food bolus and eventually that bowel movement pass through your intestines so you get better motility. And because of that, it's not hanging out in your colon as long, potentially causing, health defects. in your colon, so that leads to a decreased risk of colon cancer, less constipation, all these different things. Fiber is very, very good for your bowel health in that regard. But then there are also some other cool benefits. So as it adds bulk to the food bolus that you are eating, that helps with, digestion and moving it through your gut faster, but it also helps you absorb the food slower. So maybe that's counterintuitive, but the reason for that is just because, if you consume a lot of sugars and starches in a meal, and all you've consumed is sugars and starches in that meal, then they're going to be broken apart pretty quick, make it to the endothelium and the villi and the microvilli of your digestive tract, and absorbed very quickly into the bloodstream. However, if there is more total material in that bolus of food that's being digested, then it's going to, the sugars and starches are going to have less contact with the endothelium of your intestine, so it's going to be kind of absorbed slower. It is going to, cause less spikes on your blood glucose. Not that I really think that's bad when we have calories controlled, but, for many people who do struggle with excess food consumption and things, that could be very desirable in that regard. And then the last one, something that I kind of think is like the coolest little benefit of fiber, and it's not necessarily unique to fiber, but there's a compound that is commonly found in fiber-containing foods. For example, oats is beta-glucan. Now, this is why, maybe, have you ever seen like the box of Honey Nut Cheerios? And it's like, well, it helps lower your cholesterol. Have you ever seen that and been confused? Like, how does eating Cheerios help me lower my cholesterol? Well, let me tell you, it's because of beta-glucan. Beta-glucan is found in oats and other fiber-containing foods. And, well, first off, let me tell you about bile. Maybe you're familiar with bile, maybe you're not. But bile is a substance that is produced by the liver and stored in the gallbladder. That is the function of your gallbladder. And then it is kind of secreted into the small intestine when we eat, and food is released in the small intestine. And its job is to emulsify fats that we eat, because many of the digestive, liquids and things that we use to digest our food are water-based, and so the dietary fat that we consume is not going to mix, and it's not going to be digested and absorbed. That is where bile comes in. Well, bile is made by the liver, but then it is activated into something called a bile salt with the help of cholesterol. Now, a cholesterol in the blood, the job of a cholesterol is actually to transport fats to and from the cells and the livers and the tissues of the body. Cholesterol, their job is to emulsify fats in the bloodstream. Bile's job is to emulsify fats in the digestive tract. And so this bile needs to be activated with a cholesterol molecule to emulsify fat. However, when that happens, the bile salt, the activated form of bile, is very, very good at being recycled by the digestive system. And so the bile salt with that cholesterol attached to it, about 90 to 95% of those bile salts are reabsorbed into the bloodstream and repurposed and recycled and reused. So we're not actually losing a lot of cholesterol to bile, the activation of bile into a bile salt. That changes, however, when we consume beta-glucan. Now, beta-glucan binds to the activated bile salt and prevents it from crossing back over the intestinal endothelium. It's unable to be reused, and it will just stay with the stool and be excreted when you go to the bathroom. And so, when your body wants to produce bile again, rather than recycling the cholesterol, it has to use cholesterol from the body. It has to, so that process, when you keep using it to, create bile salts, you're using cholesterol to make bile salts, but then you excrete it, it's going to keep pulling cholesterol from the blood to create bile salts, and that is what is going to lower your cholesterol. It's just because the beta-glucan causes that bile salt to be excreted, so you have to use more cholesterol, which will lower your cholesterol. So that is why Honey Nut Cheerios can actually tell you that eating them will help you lower your cholesterol. Now, I've already kind of mentioned that if you are an athlete, I think you need to be eating carbs. It's possible to live on a ketogenic diet, but it's not something that I recommend for high performers. But then if that's the case, and we'll get into that, in just a second. But if that's the case, then why are ketogenic diets so popular? If your brain prefers, glucose for energy, why are ketogenic diets so popular? Why? If carbs are so good for you, they're so essential for brain function, all these different things. Why would you want to do a ketogenic diet? And well, that has to do with excessive carbohydrate consumption. Basically, we have seen a huge increase in the carbohydrate consumption to the point where it is excessive for the average person, because the average American eats a lot and moves very little. That, is excessive food consumption, right? So when you're consuming food at an adequate level for you, you're at maintenance calories, or even in a deficit, then carbohydrates are great for you. You're not really going to see any of these bad side effects. But just because there has been such an increase in, carbohydrate toxicity, you could almost say overeating of carbohydrates, that is kind of why these ketogenic diets have become popular, is because, well, if you completely cut out a food group, one of the 3 macronutrients, then you're really just going to limit the amount of food you eat, the number of total calories that you eat, and that could lead to a lot of beneficial health outcomes in a lot of other regards. However, that doesn't mean that carbohydrates are bad. But let's talk about why they are so overconsumed. Well, again, like I've said, calories are the heart of the issue, but lowering your carbs can help you lower your calories. Carbohydrates are just very palatable. They're very cheap. They taste very good. They're very accessible, but that doesn't mean that they're bad. Now, an example I like to bring up on this topic is that of high fructose corn syrup. Now, that is a very, very, very demonized food. High fructose corn syrup is so bad for you, everyone will say. And I actually usually kind of take the stance of defending high fructose corn syrup. Now, that's not because I think that high fructose corn syrup is good for you. I don't think it's a health food, but I usually take the stance of defending it just because it's important to me for people to understand that it's the calories that are the issue, not the high fructose corn syrup. Now, high fructose corn syrup, it's called high fructose corn syrup, but that's just because it's not like there's a low and a high fructose corn syrup. It's just because, we've made this corn-based syrup that is higher in fructose than just normal corn. Anyways, high fructose corn syrup was actually invented in Japan, I believe in the 60s or 70s, and it was adopted into the United States at about that same time, a few years later, of course. But basically what happened is that there was an overproduction of corn in the United States. As I think it was Richard Nixon, who, as a political thing to try and get votes from farmers, started to sell corn to Russia. And that let them be able to produce more and make more money. He was very popular with the farmers for that reason. However, the next president, Jimmy Carter, decided that he was going to stop that sale of corn to Russia because of, things related to the Cold War. Now, disclaimer, the facts of this might not be completely accurate just in terms of the years and the presidents and things. Because, again, I'm a nutrition guy, not a history guy. But the story is going to be about right. Anyways, after this, all these farmers were used to producing so much corn, but then, the president stopped the sale of corn to Russia. So we had incredible, excessive amounts of corn in the United States. And so what were we going to do with it? Like, these farmers were going completely poor because there was, such a high supply that demand was very little. They really couldn't charge very much for corn. They were becoming very, very poor. And we just had all this corn that we had no idea what to do with. And so this is when we took that idea from Japan of turning corn into this sweet-tasting corn syrup. And it took a while. People kind of resisted the idea at first, but it became a very, very cheap way to sweeten foods, including sodas and including, just like pastries and snacks. And this was kind of the point where those high-calorie, hyper-palatable, sweet, sugary snack foods and things in the United States started to become very, very, very cheap, because rather than using, cane sugar or, sugar produced from sugar beets, we were able to use corn syrup, which is just so much cheaper. Now, if you want to demonize corn syrup in that regard, well then, you kind of can, right? Corn syrup is what led to these hyper palatable foods being very cheap and very accessible, which is what led to an overconsumption of them and, kind of America getting fat. But that doesn't mean that high fructose corn syrup in and of itself is bad for you. And again, kind of the reason I feel passionate about explaining that is just because, for example, there's push to replace high fructose corn syrup with cane sugar in sodas. We're missing the point. I mean, maybe that's going to make soda more expensive, and then people aren't going to drink full sugar soda anymore, or at least as much because it is more expensive. Maybe that could be good. But if you go from drinking 4 or 5 cans a day of soda sweetened with high fructose corn syrup versus 4 or 5 cans a day of soda sweetened with cane sugar, there's going to be no different health outcomes at all. In fact, high fructose corn syrup is about 50% glucose and 50% fructose, which, cane sugar or sucrose is literally 1-to-1 ratio, 50% and 50% glucose fructose. So it's almost identical to the cane sugar that you would sweeten soda with alternatively. So it's really not the bad guy that many people think it is. Then lastly, I've kind of already touched on that, but another bad side effect of excessive carbohydrate consumption is that of cavities. Again, we've already discussed high amounts of sugar lingering in your mouths are metabolized by the bacteria in your mouth, leading to acidic byproducts that can cause cavities. That is another health concern of excessive carbohydrate consumption. Then the last thing I wanted to talk about before we do move into the conversation topic of alcohol is carbohydrate consumption for athletes. Now, again, we've kind of already touched on the ketogenic diet and all these different things. You can be a ketogenic athlete. You can be a ketogenic person, but especially as you get to higher intensity levels of physical activity, carbs are just very, very beneficial for you because they are the most efficient source of energy for the body. They're the most efficient. I use that word strategically. They're not necessarily, the best or anything, but efficient is the word, right? Just because the number of steps that it takes for a glucose to be used for energy is very, very little. A glucose molecule can just be broken in half, basically, to molecules called pyruvate, and then pyruvate is going to very quickly enter the citric acid cycle, and from there be used to produce ATP, the energy currency of the body. It's fast and it's efficient. Whereas fats, well, first of all, fats are stored in fat tissue. There's no really fat storage in the muscle cell or in the liver, whereas there is carbohydrate storage. That is another reason why it's very efficient. But then fats need to be mobilized from the fat tissue, and then they need to be broken off. They're long chains, 2 molecules at a time in a process called beta oxidation. And then there's a byproduct of that because fats don't have even numbers of molecules. And it's just a lengthier, longer process of mobilizing and metabolizing fats for energy. So if you're trying to sprint or lift heavy or do all these things, especially, for high intensity activities, the higher intensity an activity is, the more carbohydrates we are going to be used for energy to fuel that activity, right? So I've discussed in previous episodes, there's something called the respiratory quotient. And so that has to do with how much oxygen we are inhaling versus how much carbon dioxide we are exhaling. Now, if we are consuming depending on whether we are using carbohydrates or fats for fuel, we are going to see different numbers in that respiratory quotient. So if it was 1-to-1 ratio, that means we are consuming or using exclusively carbohydrates for energy. And then if it was a respiratory quotient of 0.7, so a 7-to-10 ratio, then that would mean we're using exclusively fats for energy. And then anywhere in the middle means we're using a mix of both. And when we're doing higher intensity activity, that respiratory quotient is going to push further away from 0.7 and more so to 1.0. That's how we know that carbs are just the most efficient and preferred energy source for these high intensity activities in the body. So Athletes should be eating carbs. And again, if you need to manipulate your body composition for, sport or athletic performance, obviously that's a very ideal thing to do. It's commonly said that, you should be doing, for example, like low intensity cardio so that you're burning more fat for fuel. And that could be very true. But obviously calories are going to be the thing that is needed at the end of the day, because regardless of where your calories come from during physical activity, you're going to burn X number of calories in a day, and you're going to eat Y number of calories in a day, and it's just the difference in that, so it doesn't much matter. But so maybe you want to consume a little bit less carbs as an athlete because you're trying to manipulate body composition and lose body fat. In that case, good. However, athletes, in my personal opinion, and definitely according to the literature, if you're seeking added performance levels, you should be consuming at least a moderate carbohydrate diet. Now, let's go ahead and move into alcohol. But before we do, I wanted to thank our sponsor of today's episode. Now, unfortunately, I'm kidding. I do not actually have any sponsors for this show, but I put this podcast on with my own time and my own money just because I have a desire of sharing high-quality scientific information with anyone who is willing to listen and wants to learn. I love putting on this podcast, and if you would like to sort of help out to be a sponsor of the podcast in your own way, there are some great zero-cost ways that you can do that for us. I'd really appreciate that. I know that everyone's always shilling at you to like and subscribe, but these actions, they really do a lot for helping the algorithms of the different platforms understand that people are enjoying the content that I make, and they should recommend it to more people. So I would definitely appreciate if you leave a rating on this show on Apple or Spotify podcasts. You can subscribe and like this episode on YouTube. You can also leave a comment on YouTube with any questions and content suggestions. I do read all of the comments that I get on YouTube. You can also share this episode or the show with a friend or family member who you think might benefit from it and enjoy it. And with that, you guys would be a huge help in helping this podcast grow, and I thank you. I do also offer nutrition and exercise coaching. If you're interested in working with a coach, that can be a very helpful thing in reaching your athletic goals. That, of course, is a for-cost way of supporting the podcast, but if that's something you are interested in, you can find more details about how to apply for that in the show notes or the caption, depending on how you are listening. With that, let's move into alcohol. So there's different types of alcohol. I've already kind of mentioned in this episode, sugar alcohols. Alcohol is sort of a term in organic chemistry, and it just has to do with different groups that are added on to a molecule. And so there's different varieties of alcohols. Sugar alcohols is one example, but there's also isopropyl alcohol. Isopropyl alcohol, use it for cleaning and disinfecting things, or I'm sure you guys know it. You can light it on fire and use it for fuel in a camping stove or all these different things. But isopropyl alcohol is not the kind of alcohol that we consume in beer and wine and, vodka and whiskey, all these different liquors. That is not dietary alcohol. Okay, dietary alcohol is ethanol. The correct scientific term for dietary alcohol is ethanol. Now, ethanol could be considered one of the macronutrients, like I talked about earlier, and it is going to contribute 7 calories per gram. Now, that doesn't necessarily mean just per gram of the alcoholic beverage, right? Just as much as that 4 calories per gram of carbohydrate doesn't mean that it's 4 calories per gram of the fruit that you're eating, but just for every gram of actual carbohydrate. And so in alcohol, there's, the label on each container of any alcoholic beverage saying what percentage by weight it is of alcohol. So if you have a liter of alcohol, and so that's 1,000 grams, then if you had, maybe it was 50% alcohol, then you have 500 grams of alcohol, and that times 7 is 3,500 calories. Anyways, there are some reasons why alcohol is bad for you. You might have heard it considered a poison, and that is how I'm going to consider it. I'm going to tell you that alcohol is a poison, and you should not be drinking it. But why do I think that? Well, first off, some of the properties of alcohol in the terms of digestion is that it does not need any sort of digestive or cellular transporters. So for example, even just to digest things like glucose and fructose, there are special protein transporters that are able to get these, sort of large molecules, from the digestive tract, the endothelium of the intestine, across the cell membranes of the villi and microvilli on the intestine so that it can actually be absorbed. There's different transporters, sometimes different facilitators. Sometimes there's a transporter that needs to be activated by sodium is a good example. So there is a sodium-dependent glucose transporter in the intestine. So if you're low on sodium, you're not going to absorb glucose very well. However, alcohol does not need any of these transporters for the digestive tract and not for the cell. So all it does is it moves throughout the body by basically diffusion, which is similar to osmosis, right? It just means if there's a high concentration in one place and a low concentration in the other place, it's going to move to where there's a lower concentration to try and even out. So when you consume alcohol, it is going to very rapidly, cross the endothelium of the intestines and into the bloodstream. And in the bloodstream, it's going to very rapidly move into the cellular tissues of the body, the muscle cells, and everything like that. So it transports throughout the body very, very fast is basically what I'm trying to say. However, in the body, there is no storage site for alcohol, right? Again, we can store fat in fat tissue. We can store proteins a little bit in the blood, but just in the muscles. We can store carbs in the liver, a little bit in the blood and in the muscle tissues. But alcohol, there's nowhere for it to go. There's no storage mechanism. So it just needs to be metabolized right now. And that actually is going to be one of the reasons why it is kind of poisonous to the body, is just because it preoccupies the liver to be metabolized because there's nowhere else for it to go. It is sort of top priority. Now, the other reason that it is bad for you is because of the way that it is metabolized. So the way that alcohol gets metabolized is, first off, something called alcohol dehydrogenase is going to work on the alcohol and lead to a product called acetaldehyde. And that is sort of one of the intermediates of alcohol metabolism. Now, that alcohol dehydrogenase is primarily in the stomach. There is some of it in the liver, but if you're just drinking a very small amount of alcohol, that is probably all going to be able to happen in the stomach. But then the more and the more alcohol you drink, especially if it's an episode of binge drinking, then a lot of that alcohol is not going to be dehydrogenized by alcohol dehydrogenase. It's going to make it into the blood, and it's going to raise your blood alcohol content. Now, acetaldehyde then is worked on by something called acetaldehyde dehydrogenase, and that is going to lead to a product called acetyl-CoA, which you might be familiar with if you know cellular respiration. And acetyl-CoA is able to enter the citric acid cycle and be used for energy. Now, the tricky part about that, though, is that acetaldehyde is actually a known carcinogen. It's carcinogenic or cancer-causing. And acetaldehyde dehydrogenase is primarily located in the cells of the liver, or the hepatocytes, you might hear them called. And so that acetaldehyde that might have been created in the stomach has to make it through the intestine, through the bloodstream a little ways before it can be transported to the liver to actually be dehydrogenized and form acetyl-CoA. Now, acetaldehyde is a carcinogen just because it is very reactive with things like DNA molecules, as well as certain proteins in cells, and that can kind of damage them, deactivate them, prevent them from doing the functions that they are supposed to perform in the body. Of course, when it damages the DNA, it also prevents that from perhaps duplicating properly the way that it is supposed to. It is really just going to disrupt a lot of different processes in the body, and that, of course, is not ideal. So acetaldehyde, the intermediate of alcohol, is a carcinogen, and it's kind of unavoidable to be produced. Hopefully it's produced and then moved to acetyl-CoA through acetaldehyde dehydrogenase very quickly, so it's not going to do a lot to you, but the more you drink, the more damage it's going to do. But then, as I've mentioned, it's also bad just because it preoccupies the liver. It is the first priority of the liver to metabolize alcohol. Now, acetaldehyde can also be produced from alcohol in the liver. Like I said, it is going to primarily be done in the stomach if you're drinking low amounts of alcohol. But if that alcohol makes it past the stomach and is in the bloodstream, then that is going to be done in the liver. Now, that when our blood alcohol content rises, the ethanol molecules themselves can have a number of bad side effects. Namely, they're going to interfere with the processes of different neurotransmitters, which is why you can get drunk and intoxicated off of alcohol. It is why, your speech is going to be slurred and your reaction time is going to be slower and you're going to, kind of act silly and dumb, just because it's the alcohol itself, before it has been made into acetaldehyde, is interfering with neurotransmitters and causing those processes to slow down. Now, as it is being processed, it can be turned into acetaldehyde in the liver as well, but then at that point, the acetaldehyde is a high priority to be turned into acetyl-CoA to be used for energy. And so as the liver is doing all these different things, you guys, maybe you know and maybe you don't, the liver does a ton of things. Like, if you kind of wanted me to sum up what the liver does in one sentence, it would be a very, very long run-on sentence, because it'd be very, very hard to dial everything down. But the liver is responsible for producing a very, very high amount of different enzymes and digestive hormones. Like I've said, it produces bile, which is stored in the gallbladder, and it is going to filter out different toxins in the body, and there's a laundry list of things that the liver does for you. And when it is preoccupied metabolizing alcohol, it is going to do all of its other jobs poorly. So, for example, vitamin D is activated in the liver. There's a form of vitamin D called ergocalciferol, or vitamin D2, that then needs to be activated in the liver to something called cholecalciferol, or vitamin D3. If the liver is busy metabolizing alcohol, it's not going to do that. There's also other processes. So like bile is something I've already mentioned. It's not producing bile, and so you're not absorbing fats as efficiently as you could. Hopefully you have a little bit of bile stored in your gallbladder, but when that runs out, you're probably not going to be absorbing fats and the lipids from your diet very well, including the fat-soluble vitamins. So like vitamin A needs to be emulsified so that it can be absorbed, and so you might not be absorbing your fat-soluble vitamins like vitamin A and E and K. So that could interfere, or that could be interfered with by alcohol, as well as your B vitamins. Your B vitamins, in a nutshell, are kind of used for energy and food metabolism as coenzymes and things like that. And there's a lot of B vitamins that are kind of wasted metabolizing alcohol when they could have been saved and used for metabolizing other things like carbohydrates and fats and proteins. And it's also a huge risk for when you're taking certain prescription medications when you're drinking alcohol with them, because the liver is supposed to metabolize and in some cases activate these medications that you're taking. But when it's busy metabolizing alcohol, there's a greater risk for adverse side effects and things like that. So there really is a ton of reasons why you should not be drinking alcohol. Now, admittedly, I have a religious motivation for not consuming alcohol, but also I am 23 years old now. I never used to really have any desire to drink underage and break the law in the United States that you're not allowed to drink until you're 21. And to that point, regardless of my religious predispositions to, my opinion on alcohol, I've kind of learned enough about alcohol that I never cared to consume it. So, I guess maybe I would feel differently if I grew up in a culture or a household that consumed a lot of alcohol. Maybe it would be harder for me to tell you these bad things about alcohol. I'm sure that I do have a bias there, and that's something that I want to acknowledge. But alcohol is not good for you. If you are seeking to be a high-performing athlete in any regard, if you drink alcohol now, you could pretty reliably improve your performance and become healthier by stopping drinking alcohol. There are lots of different arguments for why you should drink alcohol or why you could drink alcohol, and usually they kind of relate to like stress management. Now, alcohol itself is not a great way to manage your stress, but some people will kind of share a drink with a friend or a family member. And that, sharing a drink with a friend could be stress relieving for them. And in that case, that could be a good health benefit of alcohol, is just, it's something that helps you relieve your stress in a social way. But really, it's the social aspect that is stress relieving. And so hopefully, I would encourage you to find a way to have that good stress relieving social connection without the alcohol. There's also been thoughts that because you kind of get drunk and sleepy, maybe that could help you relax as well. There could be some physiological benefits, but it's really just not worth the other harmful effects in that regard. You might have also heard, but red wine, there are studies that say that, having a glass of red wine every night with dinner is good for you and helps you live longer. In fact, I've heard it described as having sort of a J-shaped curve of health. So like the more alcohol you consume, how many diseases are you going to have? And it actually is J-shaped. So as you have that first drink of alcohol a day, maybe you have less diseases, but then it just goes up and up and up from there. And that's something I want to address. There's a reason, or there's a number of reasons why we might see that effect on our health. Why is it perhaps healthy to drink a glass of red wine every night with dinner? Well, one reason is because if you're consuming a glass of red wine with dinner, you're probably not having that dinner at McDonald's, right? So you're probably having it at home with your family. There is a possibility for that, stress relieving social aspect that I've said, and you're likely to be, having better meal choices within that meal. That's just, I'm not saying that is necessarily everyone who has red wine with dinner has a healthier meal than people who don't. Like, that's certainly not the case, but it is definitely a possibility in that regard. But then there are some other things. First off, red wine is very high in an antioxidant called resveratrol. And so antioxidants are sort of anti-cancer causing, get rid of oxidative stress that can damage cell walls and damage DNA. The antioxidants are great for you. It's one of the reasons you should consume, whole grains and fruits and vegetables is for these antioxidants. And it is true that red wine is high in that antioxidant resveratrol. However, let's use our thinking brains. What else might be very high in resveratrol? What else is a dark red beverage that comes from grapes? Grape juice. If you really want it for the resveratrol and for the antioxidants, you could consume grape juice, or even better, cranberry juice or pomegranate juice. Also have very high levels of antioxidants that could be very, very good for you if that's what you're seeking after. Now, one other thing is that alcohol in the blood has a slight anticoagulant effect, which means the formation of blood clots that could lead to like a stroke or a myocardial infarction, a heart attack. Those clots that stop blood flow to perhaps your heart and your brain could be slowed, the creation of them, when there's a little bit of alcohol in your blood because it's slightly anticoagulant. That's true, but is that worth it? Is that anticoagulant effect worth all of the other bad health outcomes? The preoccupation of your liver and perhaps, the acetaldehyde being a carcinogen? Probably not. I would definitely venture to say no. And that's really all I have to say about alcohol for you today. But now that we've learned about alcohol, I want to go back to carbs for just a second. And this is the last thing we'll talk about in today's episode. But I've kind of already talked about how carbs are the most efficient use or the most efficient fuel source for high-intensity activity. It's very, very fast and very local to use carbs for energy. There are definitely some people who are very pro-ketogenic diet, pro-carnivore diet, who don't really like that. We say you should be consuming carbs for that reason. And so they kind of want to blow smoke in its face and maybe point out reasons why that doesn't actually mean anything, that carbs are the most efficient fuel source. And so one thing that I have heard is basically this. Well, you say that, carbs are the most efficient fuel source, but then you don't want to talk about alcohol, right? Because alcohol is the first priority of the liver to be broken down into acetyl-CoA and turned into energy. So like even if you have carbs, if you go and you drink alcohol, well then alcohol must be the most efficient because it's what your body prefers to do for energy. And that is a silly argument, and let me explain why. Using an analogy that I have tastefully prepared for you. Kind of teasing, but basically, let's say that you know some sort of a high-income skill. You went to college, to business school, and you have some sort of a high-income skill. Maybe it's accounting or sales or whatever. Let's just say you have some sort of a high-income business skill, and for every hour that you engage in that skill, you could make yourself $50. So you can make $50 an hour doing this high-income skill. Now, let's also say that when you were going to college to learn that high-income skill, you worked for a landscaping company. You learned how to mow lawns and weed whack and all these different things. And every hour that you did landscaping during college, you made $20 an hour. Well, so now you're graduated. Now you're living by yourself. You get to choose how to spend your workday. You can spend, your 8-hour workday making $50 an hour. You can spend your 8-hour workday making $20 an hour. They both make you money, but definitely your high income skill, whatever it might be, that makes you $50 an hour is a more efficient use of your time because for, every hour that you spend on it, you're making a lot more money. So that can kind of be compared to carbs and fats, right? It's not that you can't make money landscaping. It's not that you can't get energy from fats as a fuel source, but carbs are just more efficient. It's a better use of your time. Now, let's introduce alcohol into this scenario. Let's say that you get stabbed in the leg, and so now there's a knife in your leg, you're bleeding, you have this 8-hour workday ahead of you, but rather than using that 8-hour workday to do your high-income skill or to landscape, you choose to use that 8-hour workday to go to the hospital, to get the knife removed, and to get stitches because you got stabbed in the leg, right? Maybe this is a goofy example, but bear with me. That is going to make you no money. In fact, to go to a hospital is probably going to cost you money. So it is a very inefficient use of your time. You could have made $400 if you were doing your high-income skill all day long, but instead you wasted your day to go to the hospital. Well, yeah, but I'm sure that there's nobody under the sound of my voice who would not rather go to the hospital. It's because something has occurred that is going to damage you and cause harm if you do not get it taken care of. And that is what alcohol is, right? It's not that it's more efficient of a use of energy or time or, what have you to use alcohol as opposed to carbohydrates. It's just that it's poison. Alcohol is poison, and your body wants to get rid of that poison and take care that harmful thing that could be affecting it then, all right? You should probably not be drinking alcohol. And again, I've acknowledged my biases, but really it's just if you want to be a high-performing athlete or higher performing than you are right now and you drink alcohol, probably a good way to improve is to drink less alcohol, all right? I can understand if you want to have a drink or two a week, perhaps as a social thing with your friends on the weekends, what have you, but really alcohol is not good for you. I would encourage you to find alternatives. I do know that they actually make like non-alcoholic beer, so maybe that's something that you could enjoy the taste of and, be in a social setting with your friends where you're still not consuming alcohol. I don't know. What have you, whatever you'd like to do. I just want to present you the knowledge, I guess. Take the knowledge that I've given you and make your own informed decisions. But now you know my opinion and what I would recommend. With that is my first episode of Nutrition 101, Carbohydrates and Alcohol. Thank you, guys. I look forward to seeing you guys in the next episode. I think at this point I haven't planned, but I think we're going to be talking about proteins next, followed by fats. We'll probably have an episode for the fat-soluble vitamins, then maybe the water-soluble vitamins, and then maybe an episode or two just all about the different dietary minerals that we consume. Anyways, again, like I said, please consider sharing, liking, rating, commenting. I know I don't mean to sound cheesy as I ask you guys to do all those things for the podcast, but it really does help in a meaningful way. And if you take the time to do that, I'd be very, very appreciative. Thank you for joining me today. This has been The Science of Sports Performance.